Okay, let's continue the three-moment equation. This is a new example. What is new in this example? I have two things that are new than the two last examples. The first thing, there is a concentrated moment on a support. We didn't see this before. The second thing, that when I'm going to start the first step, I will find two redundant moments at two different supports. Let's start. What's the first step? Again, what's the first step in the three-moment equation method? Look at the supports. How many supports do I have? I have three supports, A, B, and C. Please calculate the moment at each support. Okay, so MA equal 0. What about B? MB. Can I calculate the moment at B? If I am going to calculate the moment at B from the left, I will not be able to calculate it because I don't know the reaction at A. If I'm going to calculate it from the right-hand side, again, I don't know the reactions at C. So MB is redundant, is unknown. What about the moment at C? C is a fixed support, so it's unknown. That's what I was talking about 2 minutes ago, that now in this example I have two unknowns. The last two examples, the last lecture, I was having only one unknown. Okay, what's the second step? So I know now that I have two unknowns, so I think I have to think about two equations, okay? What is the second step? Split each span. So I have only here two spans. So split each span as a simple beam, AB and BC. As a simple beam, the three-moment equation has a proof. The equation that we used last lecture has a proof. I told you it's a very long proof. But the first step, it's based on that each span has to be simple beam. Even this is a fixed support, yes. Even if there is a fixed support, when you are splitting each span in the second step, it has to be split as a simple beam, okay? Here, I have a uniform distributed load. And the span A, B, I don't have any loads on it. What about the concentrated moment at B, 3 ton-meter? Again, we didn't see this concentrated moment in the last two examples. How will I deal with the concentrated moment now if it is on a support and I am splitting each span? So where will I put this moment? On AB or on BC? This will be the question. The answer will be any of them is okay, but for sure you will not put it twice. You will put it either here on AB or here on BC. Okay? But usually there is a better decision, a better solution. The better solution will be, please put it on the span that have the least loads. Here I have a span without any loads, empty span, and here I have a span with a distributed load. So what will be the best decision now? Where to put the concentrated moment? On AB or on BC? So here we have to put it on AB. Take care. What is the direction of the moment? It's anti-clockwise, right? So take care when you put it on the other span, it has to remain in in the same direction, anti-clockwise. So when you put it on the span AB at B, it has to be like this. No one come and tell me and ask me, oh, why? Here, the moment the tail is upwards, and you are now putting the tail downwards. It's not a matter of the tail, it's a matter of the direction. The direction has to be the same. Here it's anti-clockwise, here it has to remain anti-clockwise. If you are deciding to put it on the span BC, again it has to be on the same direction. So the anti-clockwise on the span BC will be like this. The tail will be upwards. So it's not a matter of the tail, it's a matter of the direction. Okay, what's the third step? I have to draw bending moment diagram for each span. Let's draw the bending moment diagram for each span. Here, the moment EL squared over 8, so 4 squared divided by 8, which is I think 4, yeah. This is the bending moment diagram. Put it on a conjugate beam. That will always be a simple beam, because the three-moment equation is based on when you split each span, it has to be a simple beam, and the conjugate beam of the simple beam is always a simple beam. Calculate the areas of the moments. I have only one area. The area of the parabola is 2 over 3 base 4 meter times height, which is 4. Only the area, no, it's divided by the inertia factor, which is here 2. So this will be 5.33, I think. Let's double check. 5.33. Anyone double checking? So the reaction here, it's in the middle. So the reaction here will be half. Is it right? 5.33. I think it's right. 4.33. Okay. So this will be 2.67, and this reaction will be 2.67. This point is C and this point is B. Okay. What are these called? What are these reactions called? We said last lecture, these reactions are called elastic reactions. Elastic reaction. What's the definition of the elastic reaction? It's the reaction from the conjugate beam. You know this expression, elastic reaction, since the mechanics of materials, the deflection method. Okay? Let's repeat it again on the span AB. What will be the bending moment diagram for the span AB? It's so easy. The moment at A is 0, and the moment at B is 3. So this will be the bending moment diagram for the span AB. Put it on the conjugate beam. And then area, it's a triangle downwards, so it will be downwards. What's the area of the triangle? Half base times height, half. Base is 3 meter, height is 3 meter, and inertia factor is 1, so it will be 4.5. How can I calculate these reactions? How can I calculate the reaction? Here that was easy, right? It was in the middle, so half and half. But here the triangle is not in the middle, so it's not half and half. How can I calculate the reaction? Easy, like structure 1. Take a moment at any point and calculate the reaction. We'll say like 4.5 times 2, and y, I don't know what's the value of the y, times 3 equals 0. So, but this is easy. I can know it without any calculation, because this is 4.5 and it's in the 1/3 and the 2/3. So automatically this will be 3 and this will be 1.5. But if there is like any advanced reaction, so the basic is structure 1. Take a moment at any side and calculate the reaction on the other side. Okay. A and B. What's the next step? The next step is the last step. Okay. But we have to concentrate here. Apply three-moment equation. Last lecture, we were having 2 examples. Both of them was having only one unknown. Here I have 2 unknowns. The rule is apply three-moment equation at the point that is having an unknown moment. So the last 2 examples, we apply three-moment equation only once at the unknown moment of the support. Here I will apply the three-moment equation twice. Once at B and once more at C. So let's start with B. Apply three-moment equation at B. Take care when applying, okay? Where am I now? I am at B. I am here. Just remind yourself where you are. You are at B, okay? Okay, so the equation is 2mb. And the span before, what's the span before? It's 3. Divided by the inertia factor is 1. Plus, you are still here. The span after, it's 4 divided by 2. Plus and plus. What is the support that is before B? It's MA. And what is the support that is after B? It's MC. And bring this here, 3 over 1. And this on the other side, 4 over 2. This will be the left hand side. The right hand side, -6 multiplied by R. I am at B, so it will be RB. MA here equals to 0. MB is unknown, MC is unknown. What about RB? RB is the elastic reaction at B. The elastic reaction at B. From the left hand side it was 3. From the right hand side it was 2.67. So RB is 5.67. So 3 plus 2 is 5. 5 times 2, so 10 MB. 10 MB plus 2 MC equals to -6 times 5.67. I think it's -34. I think this is the first. Yeah. So this is the first equation that has 2 unknowns, MB and MC. So now I have to apply three-moment equation one more time at the support C. So where am I now? I am here. Take care. We are applying here at C. So the equation will be 2mc. The span before it is 4 divided by inertia factor is 2. What about the span after? No span after. There is not any span, so plus 0. Okay? Plus and plus. What is the support that is before C? It's B. What is the support that is after C? No support. 0. Bring this here, 4 over 2. And this will be be equal to negative 6 or C, because I am applying at C. Where is RC? RC is only 2.67. So RC here is 2.67, and here it's 2 MB plus 4 MC equals to negative 16. This is equation number 2. Can I solve these two equations? Yeah. The answer will be MB will equal, so here, from 1 and 2, MB will be equal to negative 2.89 ton meter, and MC will be equal to negative 2.56 ton meter. So now we want to draw the bending moment diagram. I have two spans, span A, B, and span B, C. MA equals to 0, MB equals to negative 2.89, negative means it's upwards, and MC is negative 2.56, negative means upwards. But I have a problem here. There is a concentrated moment at B, which is 3 ton meters. Structure 1. How do I deal with a concentrated moment inside the beam? I have to calculate the moment 2 times, right and left, and I have to put the two values on the bending moment diagram, and there's like a drop in the bending moment diagram when there is a concentrated moment. So the question is, the 2.89, is it MB right or MB left? This is the main question now. And if I knew what direction is it, so I have to calculate the moment in the other direction, and then I can do the bending moment diagram. So the first question, the 2.89, is it MB right or MB left? It is the moment from the side that you did not put the moment at. Where did you put the moment? On the span AB, which is left. So the MB here, it's MB right. Now I have to calculate MB left. How do I calculate MB left? I don't have the reaction. How do I calculate MB left? It's easy. I now know that this is point B. The right is 2.89, the tail is above. And the moment itself, put it away like this, it's 3 anti-clockwise. So what will be the value of the left in order for the sigma moment to be equal to 0? So here it's 2.89 and here it's 3. So this moment has to be 0.11. So 2.89 and 0.11, 3, and 3 on the opposite direction. So sigma moment equals to 0. So now I knew that MB left is 0.11 downwards. How will I join? I have here a moment of 0. I have here a moment of 2.56. Will I join the 0 with the 0.11 or with the 2.89? Structure 1. All of this is structure 1. All of this last 10 minutes is structure 1. Okay? Structure 1 told me that join the MB left with the left side and the MB right with the right side. So the left is 0.11, so I will join it with the left side. Why I join the solid line? I used to join a dotted line and then either there's a P square over 8, or if there is the concentrated load, so it will be PL over 4, like the last example. But here the span is not loaded with any load. So why I join a dotted line? I am sure that it's a straight line. No any other corrections. Okay. But for the span BC, there is a uniform distributed load. So I will join it dotted, and then I will make my correction. There is a PL square over 8. Don't waste the time to calculate it again. It has to be here 4. So this will be the bending moment time. What about the shear force diagram? In order to draw the shear force diagram, like the last lecture, I have to first calculate the reactions. How do I calculate the reactions? The same way, split each span like this, AB and BC. Here I have 2 times 4, 8 in the middle. Okay? And here I don't have any loads. What about the moments? I have at B 2 moments. When I am going to deal with BC, which is right, so the MB right was 2.89, but the moment was upwards like this. And when I am going to deal with the span BA, the moment will be left, which is 0.11 with the tail under like this. And the moment SC, it's 2.56 upwards. Okay? Let's calculate the reaction. So 8 in the middle, this will be 4, and this will be 4. This one doesn't have any loads. What about the difference in the moments? Let's start with the easy one. The difference in the moments here, it's 0.11 and there is 0. So the difference in the moments is 0.11 minus 0 divided by the span, which is 3 meters. So there will be here 2 forces making a couple opposite to each other in the opposite direction of the moment. The direction of the moment is anti-clockwise. So the 2 forces here will be in these directions, making a couple opposite, so it will be clockwise. The value is 0.11 minus 0 divided by the span, which is 3. 0.036. 0.036. What about here? The difference in the moments, 2.89 minus 2.56 divided by the span 4. Which moment is bigger? This one is bigger. So the 2 forces that are making couple has to be in the opposite direction because the biggest moment. So here it will be upwards and here it will be downwards. This will be 2.89 minus 2.56 divided by the span 4. 0.0823, and this is 0.083. Okay, so here I have only one reaction, so YA equals to 0.036 upwards, and YB 4 and 0.083 upwards, and 0.036 downwards. So sigma will be upwards. So YB will be equal to 4.083 minus 0.036. 4.047. And YC 4 upwards and 0.083 downwards, so we have to subtract them. So YC will be equal to 3.917. Then I will have to put the reactions here. YA 0.036, YB 4.047, YC 3.917, and here there is 2 times 4, 8, and now I can draw the shear force.